Hello everyone, my name is Adam Biehl. I'm a graduate student at Clemson University completing my master's. And I'll be talking about a project we're working on right now on the development and evaluation of a UHPC-based high friction surface treatment for pavement and bridge surface rehabilitations. This is a project I'm working alongside a PhD student, Cal Mager, and our advisor, Dr. Prasad Rangaraju. Quick outline for this presentation, what I'm going to cover. First will be an introduction, just the basics of HFSTs and UHPC. Then I'll go into the materials that we selected for our work. Next, I'll go into our continuous particle packing, where we were optimizing to try to find repeatable UHPC mixes for this work. Then I'll go into some surface properties, where we've been testing different surface application methodologies and how they reveal microtexture. Then finally, I'll be talking about the future work for this study, looking at shrinkage and abrasion resistance primarily. So a quick introduction to what HFST is. Really simply, an HFST is just a roadway surface remediation technique that we use to improve the coefficient of friction on a roadway. Typically what happens is that you'll use an epoxy-based binder in a very thin section, and you'll place a high-quality aggregate on the surface, typically hand broadcasted and embedded by its own self-weight. This is typically going to be calcined bauxite just due to its high abrasion resistance and good macro and micro texture. And what happens is, when you have a roadway that has insufficient friction, there's going to be a lot of conditions where you don't have enough stopping time and you end up crashing. However, with an HFST, you're given more time to respond because you have a greater coefficient of friction, meaning it takes less time to stop. And therefore, hopefully, you're either avoiding a crash entirely or you're significantly decreasing the severity of that crash. And that's been proven based on Federal Highway Administration and SCDOT data, where the Federal Highway Administration found that wet weather crashes were reduced by over 80% and total crashes were reduced by 53%. SCDOT data backs that up with a 73% reduction in crashes. So the main question becomes, how do we apply these to more situations? Because obviously it'd be good to do it everywhere, but calcined bauxite and epoxies are very expensive materials and are limited in supply. And to look at that, we need to look at how we can decrease the cost of linear feet as well as make them more materially available. And we've been looking at different binders to do that. And the one that we've been specifically working on is looking at UHPC. Most of you know what UHPC is. It's just a class of cementitious composite that's detailed by its high compressive strength, high fluidity, high bond strength, as well as really good abrasion resistance. What this is good for an HFST is that it matches the same criteria that's needed. For an HFST surface, you want to make sure that you have a really high bond strength, that way you're not seeing delamination from the surface and that you'll have an extended surface life. You're going to have low shrinkage and cracking, which is more so brought together by the fibers of these mixes that don't allow for it to ravel apart. And then finally, you want to make sure that you have a high abrasion resistance so you have a longer surface life. You're not losing aggregate on the surface. What's good for UHPC binders but isn't necessarily necessary is that ultra-high compressive strengths. Most HFST specifications specify 1 to 5,000 KSI compressive strengths at 1 day and 7 days respectively. So UHPC is good in terms of compressive strength. It's going to be a factor that kind of carries along based on the other properties that we want. And we made some decisions during our material selection that kind of went to sacrificing compressive strength so that we could get a little bit more bond strength, as well as make it more materially available. First thing that we used is a type 3 Portland cement for this work. That was just to ensure that we'd have that initial strength gain so that we didn't have to worry about being able to close for a longer duration than a typical HFST. These are only going to be closed for 1 day, and then we're going to be opening them up back to traffic. We want to make sure that we can match that. Secondarily, we did 3 different silica fumes because we were going to complete continuous particle packing methodologies. And we want to make sure that we had different particle size distributions so that we would have a variety of sources. We want to make sure that when you're optimizing, it's not going to be just good for one situation, it's going to be good for all. So that gave us some variability for that testing. Third is we used calcined bauxite. Calcined bauxite was just the HFST aggregate we used for the study. We hand broadcasted it for some work, but we also intermixed it in our mixes for some work, and those led to some very different mixes that I'll explain more later. And finally, we used a manufactured sand as opposed to a silica-based sand. This is a crushed granite in both a pond fines and a typical fine aggregate gradation, which we sieve between the 16 and 200 sieve, just to control our particle size distribution in our aggregate fraction. And finally, we used a high-range water reducer that had a high initial fluidity, but then significantly lost that fluidity quicker than other commercial high-range water reducers. And this was just done again to make sure that we were opening quicker. We were working at extended setting times. Now we start to shift over to looking at continuous particle packing to make sure that we had repeatable UHPC mixes as a methodology to kind of help those consumers when they're making their own. We start off by looking at a modified Andreessen and Anderson method to make sure that we had, and to do that methodology, you're essentially looking at a cumulative percent finer than for a certain size of aggregate, or sorry, constituent material. And typically we're going to control a Q value to change that proportion. And for UHPC, that's typically in between 0.2 and 0.37. And the process is pretty simple. You'll input all your different particle size distributions. You'll add a curve that you see in black here. That's going to be your particle, that's going to be essentially the line you're trying to match. And then you'll match proportions based on their different particle size distributions. We ran this for all 3 different silica fumes, and what we ultimately come up with is 6 different mixes, where we're controlling 2 variables. First one being that silica fume type, which controlled the dosage of cement, silica fume, sand, and the pond fines. Then also we did different high-range water reducer dosages at 3.5% and 4.5%, which we got from previous research that we conducted just looking at all of our background information, and this was going to achieve sufficient fluidity. Finally, there's a final variable that will be kind of left versus right on this presentation, which is our calcine bauxite to cementitious material ratio. And that was controlled at 3 to make sure that we have a dense matrix, essentially simulating hand broadcasting when we're intermixing intermixes. And for that, we can kind of see the 2 different ways that it works out in terms of volume. So on the left, we have just the UHPC matrix without calcine bauxite. On the right, we have the UHPC matrix with calcine bauxite. And 50% of that volume ends up being calcine bauxite. So for these mixes, we end up with a cementitious material content of about 450 kilograms per meter cubed. On the left, it's about 900, and on the right, it's about 450. So different, but the same proportions outside of calcine bauxite. And this, when we look at workability, leads to 2 very different results. On the left, we see our workabilities via the modified flow table test, pretty typical for UHPCs, and generally want to be around a range from 100 to 150% flow. For our mixes, we were slightly above and slightly below that, giving us a little bit more breadth of work. On the right, we have our intermixed calcine bauxite mixes, and those were done via the more standard flow table test, where you're dropping the table, and we're seeing flows between 5 and 15%. So drastically different materials because they have a significant amount of coarser HFST aggregate in the mix. Next, if we're going to look at the main property that we care about in terms of strength, it's going to be our pull-off strength. We want to make sure that these materials are bonded to the substrate material. For our substrate, we bonded it. We did a surface preparation of essentially an ice-to-ice surface 5, and we conducted 7-day testing based on the based on the HFST specs brought to you by the SCDOT, where you wanted a 250 psi strength at 7 days. If we look at our epoxy here at the bottom, reference node that we went off of, those had strengths of about 315 psi at 7 days. Versus our UHPC mixes alone, we're somewhere between 300 and 400 psi. So really good, being that we're exceeding epoxy in some situations. However, when we go to intermix mixes, what we're seeing is that we're seeing a decrease in strength. Obviously, we have less paste, and these mixes weren't optimized for volume yet. That's some additional work that we're working on now. So there's some additional voids in the system. And that's going to be kind of our main focus of future work, as we saw reductions that kind of pushed it outside of that acceptance criteria, which means that additional work is needed if we want to use intermix mixes for real surfaces. Next, and is the part that's kind of weird for this work, is the sacrifice we made in compressive strength. Because we were using more available materials that had less inherent compressive strength than silicious-based sands, we were seeing for our per UHPC mixes, compressive strengths between 12 and 16 KSI, which is below most UHPC specs, especially ACIs at 21,000 PSI. Versus our intermix mixes were between 15 and 18 KSI, meeting ASTM specs but not meeting ACIs. We think that we can get closer to that 21 KSI mark by optimizing our HFST fraction, as those mixes had a significant pore volume, air void content, as well as they did not contain fibers, which we'll be doing optimization for as well. Some preliminary results that we did with using steel fibers indicated that we would get about a 15 to 20% increase in our compressive strengths. So we're hoping that'll carry out as well for intermix mixes. Now moving on to the second half of our work, which was looking at different surface method comparisons. We first start off with our comparison that you can see here in yellow, which is just the typical HFST surface, done using epoxy with hand broadcast aggregate. Then for the blue, we have all of our different surfaces that were prepped via hand broadcasting for UHPC surfaces. We did some testing on SSD versus oven dry aggregate, but it was found to be a negligible impact, so I didn't do any specific analysis for this presentation. And finally, we have all different surface retarders that were applied to the surface of intermixed mixes, and we used a pressure wash after 12 hours to remove some portion of the top paste. What this allowed for was the exposure of microtexture after that time period. And what we can see here is if we look at different scans that are ordered based on their magnitude of of texture, what we can see is the resin base obviously did the best. It's a very thin layer of binder with lots of surface texture exposed. Then we have our highest grade of surface retarder. Then we have our broadcast mixes with the second highest grade of retarder intermixed between those. And then we have our lower grade retarders. And for those lower grade retarders, we found that they weren't yet matching the same level of penetration depth because our density of our matrix was greater, not allowing for that same penetration, meaning that that cementitious matrix was essentially setting. Then we looked at doing laser texture scans on these surfaces just to better characterize their profile depth. We set a minimum target of 1.5 millimeters of the distance between our peaks and troughs. And we found that our resin-based system still again performed the best, and that 200 retarder, or highest grade retarder, formed second best, being statistically comparable to the resin-based system, but also being statistically comparable to our broadcast and our second highest grade retarder. Just kind of indicating that they're similar but not the same. We also completed bridge pendulum test results for this section, but they were very comparable, and most met that threshold of 70 BPN, so I didn't include it just to be succinct today. So if we want to make some preliminary conclusions from this work, first and foremost is that we believe UHPC has the potential to act as an HFST binder, but additional testing is needed specifically in terms of abrasion resistance as well as shrinkage, and that's probably going to be our main deviation from epoxy binders in the long run, is making sure that we are controlling our shrinkage, because these really thin layered binders of UHPC could crack and cause failure earlier. Second is that a continuous particle packing methodology provides comparable results between different mixes, essentially just saying that this is a methodology that you could tell your contractor that if you use this to design your mix, ultimately it would work out, hopefully well. Obviously doing some verification. Third is that intermixed calcine bauxite results in a decreased bond strength, something that we're going to verify doing some other packing methods, looking at lower calcine bauxite contents to see if that's only true for higher dosages. Next is looking that UHPC and epoxies provide comparable bond strengths, essentially saying that if we're only looking at bond strength, they are we're either getting better or equal to comparisons. And found that intermixed calcine bauxite meets comparable mean profile depth, meaning that this might be an additional methodology that's viable for creating HFSTs. Some future work that we're looking on for this project is finally finishing up some continuous packing work on abrasion resistance and shrinkage that's ongoing now, and I'll be testing it next week. We'll be doing some discrete packing work, looking at optimizing that HFST fraction, doing a lot of work on bond strength and shrinkage. We're doing some additional shrinkage testing at the early stages using the thin layer apparatus to look at the crack risk and also optimize fiber additions to decrease that cracking potential. And finally, we've been doing surface studies looking at the surface life extended through for 3-hole polishing via 3-hole polishing using laser texture scanning and DFT measurements to quantify that. From there, if you guys have any questions, I'd be more than happy to answer them. And I want to thank the SCDOT for sponsoring this research, as well as the National Brick Research Center for helping us complete some testing, and all these companies that provided materials for us. Thank you.